Question 5. Two wires, A and B, are made from the same material and are suspended vertically from the same steel beam. Wire A has a length L and a diameter D. Wire B has half the length of wire A and twice the diameter of wire A. Equal masses are suspended from the bottom of both wires. Both wires obey Hooke's law as they are stretched by the weight of the masses. What is the ratio of the extension of wire A to the extension of wire B? We can see that this is a problem that focuses on Young's modulus and elastic properties of materials. Before solving the problem, let's recall what we know. We know that for a wire stretched within its elastic limit, the extension, delta L, is related to the load F, the original length L, the cross-sectional area A, and the Young's modulus E by the formula delta L equals FL divided by AE. We also know that for a cylindrical wire, the cross-sectional area depends on the square of its diameter. Specifically, the area A equals pi d squared divided by 4, so the area is proportional to d squared. With these facts in mind, let's move on to tackling the problem. We begin with the extension formula. Delta L equals FL divided by AE. In this problem, the same masses are suspended from both wires, so the force F is the same for both wires. Also, the wires are made from the same material, meaning the Young's modulus E is the same. Because F and E are constant, we can say that the extension is proportional to L divided by A. Next, we express the area in terms of the diameter. Since A is proportional to d squared, we substitute this relationship. This gives delta L is proportional to L divided by d squared. Now we compare the extensions of wires A and B. The ratio of their extensions is delta L for A divided by delta L for B equals LAA divided by DA squared, all divided by LB divided by DB squared. This is manipulated by reciprocating the denominator fraction and multiplying with the numerator fraction to give LA divided by DA squared, multiplied by DB squared divided by LB. Next, we substitute the values given in the question. For wire A, LA equals L and DA equals D. For wire B, LB equals L divided by 2 and DB equals 2D. Substituting these values gives delta L for A divided by delta L for B equals L divided by D squared, multiplied by 2D squared divided by L divided by 2. Now we simplify. 2D squared becomes 4D squared, so the expression becomes L divided by D squared multiplied by 4D squared divided by L divided by 2. Dividing by L divided by 2 is the same as multiplying by 2 divided by L. So this becomes L divided by D squared multiplied by 8D squared divided by L. The L terms cancel and the D squared terms cancel. This leaves 8, so the ratio of the extensions is delta L for A to delta L for B equals 8 to 1. This is our final answer. What did we do? We started with the equation that relates extension to force, length, area, and Young's modulus. Since both wires experience the same force and are made of the same material, those terms cancel when comparing them. This allowed us to express the extension as being proportional to length divided by diameter squared. Then, we substituted the given relationships between the lengths and diameters of the two wires and simplified the ratio. Having finished, let's recap to finalize our solution. For a given material, Young's modulus remains constant. For circular wires, the cross-sectional area increases with the square of the diameter. And using proportional reasoning allows us to eliminate constants and solve comparison problems efficiently.